Now, under the multiplication of vectors, we will consider the vector product, which we also call the cross product or the outer product of vectors. So again, we will go to two vectors, and let's say we are having two vectors. This is vector A and this is vector B, is we consider in the case of the inner product, the dot product. This is the angle between the two vectors, which is theta. And now what we are doing in the cross product is, you remember in the scalar product, we found the contribution of one vector along the other vector. That was the form of interaction between the two vectors under multiplication. Now, in case of the vector product, we will sweep this vector along this vector, or the other case, we will sweep the other vector along this vector. So this is kind of sweeping one vector along the other vector, and area is involved here because one vector will sweep some area. And now A cross B will be area, in fact, while A dot B wasn't area. So A cross B means whenever there is dot, it is translation, and whenever it is cross, it is rotation, it is sweeping. So A cross B, and this will be equal to this area, the area which will be the area of a parallelogram here. And here is, I see that the perpendicular component here is responsible for this one. And we have calculated that in the dot product, it was the base component, the cos theta component, which was responsible. And in this case, in the sweeping, it is the perpendicular component which is responsible. And due to that reason, I will write the magnitude of A and the magnitude of B and sine of the angle between the two, as I have already written in the case of the inner product, the scalar product. So it gives you the area of this parallelogram here, and this is area. Now if I sweep this vector along B, means A along B, then the area which is here is having this direction. And if I sweep this vector along this vector, so it will be the area which will be inward. So this will be equal to the n unit vector. N unit vector is actually this area which is swept, and this will be the direction of this vector. Now in this situation, A cross B will be equal to minus time B cross A, because when A is swept along B, then this is the direction of unit vector, and then that is the direction. So both the direction are opposite to each other, and that's why we will have to write the minus sign, and that's why we say that the cross product is not commutative, as minus sign is coming here. So it is not commutative. Now I can take the example of dot and cross product in the form of screw and a nail. This is, let's say, if we are having a nail, and that nail, if we are just striking with the help of hammer, then this nail, if the hammer is exactly perpendicular over it, means in the same direction as the nail is going in, means they are parallel to it. Both the hammer means the force direction and the direction of this nail which is going in, then maximum, it will go maximum, let's say, into the wood or another material. And this is the example of dot product because it is the translation of this one. And in the cross product, if we are having a screw instead of a nail, if we are having a screw, and what I'm actually doing with the screw, I'm just rotating it this way or that way, means I'm not applying force. I'm not applying force means in the same direction, but I am applying force perpendicular to that direction of motion. And what will happen, that I apply force this way, it will move up. I apply force this way on this side, it will go into this one. So that is the screw example is for the cross product. So when I talk of n unit vector, then n unit vector is perpendicular to vector A as well as vector B, and also perpendicular to the plane containing A and B. Means this is the plane, like board is the plane in which vector A and B are there. So n unit vector will not be part of it. It will be perpendicular to it this way or the inside way. And this is the cross product. If I write, let's say, 3 vectors, and A cross B and C vectors are being added, so this is equal to A cross B plus A cross C. Means if we are having a cross product between 3 vectors such that 2 of the vectors are being added, so if they are added first, means their magnitude, their addition here, so it will be another vector, and then its cross product with vector A, it will be equal if we take cross product with one vector and then cross product with another vector and then we add those vectors. So it means that cross product is distributive. Cross product is distributive in its properties. Similarly, if I have the same vector, like for example A cross A or B cross B, now what will, according to the equation, it will be A and sine, as they are parallel vectors, they are the same vectors, so angle is equal to 0 and we will have A cross A equal to 0. Now the reasoning behind it is this one, that it is the same vector, so there will be no swept area between the same vectors, and that's why the swept area is equal to 0. And further, in the cross product, let me consider the examples. And let's say, means cross product, wherever we will have cross, then it will be the rotational dynamics. The example of torque is here. Now we know that torque is force. Torque is the rotational force R cross F. Now when F is linear force, F is inside translational dynamics regime, while torque is in the rotational regime. When we apply force, it will displace an object from one point to another point. When we apply torque, then it will rotate that object around a certain axis. This is the distance from the axis, which we call the moment arm. So torque is a force, but in rotational dynamics. If we increase force, torque will be increased. If we increase the moment arm, then the torque will also increase. So both of them are playing a critical role. So it will be equal to R F and sine of theta in the direction of this torque. So this torque will always be perpendicular to R, will always be perpendicular to F, and will be perpendicular to the plane containing R and F. Similarly, we can have the example of angular momentum, which is R cross P. P is the linear momentum. So these are just, the cross is converting the things from the translational dynamics to rotational dynamics. Now in the dot product, I have given the example that we write the work is Newton meter, and the dimensions Newton meter we write is joule. But what about this one? What about torque? So for torque, we are having R in meter and F in Newton. So this is again Newton into meter, but we will not call this thing is joule, because we know that this Newton meter, this meter dimension is due to the rotational dynamics. It is the rotation around a certain axis, and that's the reason that this one length dimension will come as extra in rotational dynamics, and we will not call this thing equal to joule. So these are two different types of dynamics. So this was the story of the multiplication of vectors. We can have multiplication of a vector by a scalar. So the scalar will only multiply with the magnitude of the vector, and it will have nothing to do with the direction of a vector. We can have the dot product, and dot product occurs in case of translation of a vector. And then we are having the cross product, which we call the vector or the outer product. And in this product, we are having the sweeping of one vector along the other vector. So it will always make an area, and that area will have either the direction outward or inward, and then the direction will be perpendicular to the one vector, the participant, and the other, while also perpendicular to the plane containing those vectors. So this is the story of the vector multiplications. I will reiterate. If you want to go into further details of this one, then in the conceptual physics series I have made a complete video series on the translation and rotational dynamics, and over there many things will become clear between the two dynamics. They are the same things, but the dynamics are different, like the torque, moment, and moment of inertia. All these things have been explained there. Another important thing is that when we will decide that we will have to use the dot product or the cross product, so it depends on the physical quantity. Whether the physical quantity is under the translational dynamics or it is under rotational dynamics. Like, it will be the result. What is the result of that thing? Like, if it is torque, then it means it is rotational dynamics, so we will have to use the cross product. If it is work, then it's a scalar quantity and it is a translational property, and we will use the dot product. So it depends on the nature of the physical quantity, that what is the result of the interaction of two other physical quantities, and based on that thing we will decide whether we will use dot product or cross product.